All right, so today we're going to be taking a deep dive into the subatomic world.
Oh, buckle up.
Yeah, you know those tiny little particles inside atoms, protons? We're going to talk about them, specifically this puzzle that physicists have been, really stumped on for a long time, which is proton spin.
Yeah, proton spin.
Proton spin, what is it? Where does it come from? What's going on?
Yeah, it's like, it seems so simple at first, you know? Like, we know protons have spin, but when you really start to think about where does that spin come from, it gets really, really complicated.
Yeah, it's like watching a figure skater, spinning so gracefully. But then, if you had to calculate the movement of every single part of their body that was contributing to that spin,
Yeah.
it's like, oh my gosh, that's a lot.
Yeah, that's a great analogy because for protons, it's kind of like, you have the quarks, these even tinier particles
Right, even tiny.
that make up the protons and neutrons. And for a long time, scientists thought, oh, proton spin, it's just the sum of the individual spins of all the quarks. But it turns out it's way more complicated than that.
It's not that easy, huh?
Not at all. So there's this other layer to this whole puzzle, and that is the motion of the quarks
Okay.
inside the proton.
How they're moving.
Yeah, so think of it like planets orbiting a star
Right.
while the whole solar system is moving through space.
Right.
The quarks aren't just spinning, they're also zipping around inside the proton in this really complex dance.
I see.
And so it's that motion, that transverse motion that researchers are now realizing plays a really key role in proton spin.
So it's not just that they're spinning, it's how they're moving within the proton as well that all adds up to the overall spin that we observe.
Exactly. And what's really cool is that scientists have actually developed this brand new theoretical approach to actually calculate the 3D motion of these quarks inside a proton,
Okay.
especially for those tricky low momentum quarks. And this is huge because previous methods, they just weren't really accurate enough to give us a really clear picture.
So we're getting more precise.
Way more precise.
So we can actually, see what's happening.
Yeah, and predict how these quarks are dancing around inside the proton.
For the first time.
For the first time. And here's the thing that gets me really excited. This new approach, it's not just some theoretical exercise.
Yeah.
It's actually already lining up with existing experimental data.
Really? So it's accurate.
It seems to be incredibly accurate, which means it gives us a lot of predictive power for future experiments.
Oh, I like that. Predictive power.
Right. And so, there's this incredible new facility that's being built called the Electron-Ion Collider, EIC for short.
Yes. The EIC, I've heard whispers of this.
At Brookhaven National Lab. And this is basically smashing atoms together at super speeds.
Like that, yeah.
Yeah. And so they're going to be smashing electrons into protons at incredibly high energies, which is going to allow scientists to study the inner workings of these protons like never before.
So this is going to, blow everything wide open.
Oh, yeah.
And this research we're talking about now will be essential to interpreting that data.
Absolutely, because it gives us that baseline to work with.
So it's almost like we're getting a decoder ring for what we're about to see.
Exactly, like a blueprint to help us understand the structure of matter.
It's like a cheat sheet.
It is. For the universe.
We're talking about the very building blocks of the universe here.
I am getting chills.
It's exciting stuff.
We're just getting started.
Just getting started.
Okay, so this new approach, I know it involves some pretty heavy-duty physics. We're just talking about quantum chromodynamics.
Yeah.
Is that even something that's explainable to, a normal person?
Yeah, I'll try my best. So, quantum chromodynamics, QCD, we call it for short. This is the theory that describes the strong force.
Right.
So the strong force is one of the 4 fundamental forces in the universe.
Okay.
And it's what's responsible for holding those quarks together.
Like super glue. For those subatomic particles. But here's the thing about QCD. The math is ridiculously complicated.
Yeah, I can imagine.
Especially when you're trying to model something as intricate as, the movement of quarks.
Oh, yeah, like those tiny little things.
Yeah, it's like trying to, map out the choreography of a ballet with, a billion dancers all moving at the speed of light.
Okay, I already have a headache.
It's tough stuff.
So how did the scientists who made this breakthrough even, crack the code? What was their secret weapon?
So they use this technique called lattice QCD, and it involves running simulations on supercomputers.
Okay.
So imagine a 4D grid, right? Representing space and time.
Okay.
And on that grid, they simulate the interactions between quarks and gluons.
Oh, wow.
Gluons are the particles that actually carry the strong force.
Okay. It's like they're creating a virtual universe inside the computer.
It is. It is. And the real breakthrough here is that they developed this new approach that really simplifies these lattice QCD calculations,
Oh,
which makes them more accurate, especially for those, pesky low momentum quarks.
right. Those were the troublemakers.
Yeah, they were like causing all sorts of problems.
Those little rebels.
So it's like, I don't know, finding a shortcut through a dense jungle, basically.
I like that analogy.
Yeah.
I gotta say, like, all this talk about supercomputers and simulating the universe, it makes me feel like we're living in a sci-fi movie.
I know, right? It's crazy.
It's pretty mind-blowing.
It really is. But, what's really exciting is what this new level of accuracy means for actually understanding proton spin and, the bigger picture of how matter works.
Yeah, let's dive into that a bit more.
Okay.
So we talked about the Electron-Ion Collider, the EIC, earlier. What kind of experiments are they going to be doing there, and how will this new research help them make sense of all that data that comes out of it?
So the EIC, this is going to be like a total game changer for nuclear physics.
Okay.
Basically, imagine these beams of electrons and protons, and each one is carefully prepared with a specific spin.
Okay.
And they're smashed together at nearly the speed of light.
Wow.
So it's like, microscopic demolition derbies, but with a purpose.
Yeah, very intentional demolition derbies.
Yeah,
I'm
exactly.
assuming those collisions produce a lot of, debris.
Yeah, you get this shower of particles that comes out, and scientists can analyze those particles to study, the internal structure of the proton with incredible precision.
So we're getting down to the nitty-gritty.
We are.
So how does our newfound understanding of quark motion fit into all of this?
Well, remember that, intricate transverse motion of quarks we talked about? That dance inside the proton?
Yeah, their little dance party?
Yeah, well, the EIC will actually be able to measure that motion with, crazy accuracy.
Oh, wow.
And by comparing that experimental data with, the predictions from these new lattice QCD calculations, we can actually test our understanding of how those quarks are contributing to proton spin.
Oh, so it's like we're checking our work.
We are. It's like having a blueprint that we can check against the actual construction.
Yeah.
So we're making sure that our theories are actually reflecting reality.
They're not just living in some mathematical vacuum.
Exactly.
Yeah.
Exactly. It's like connecting the dots between the theoretical world and the actual experimental world.
Right, right. Making sure that they match up.
Yeah. And this understanding, it could have implications way beyond just proton spin. Think about it. This could help us unlock secrets about, the origins of mass,
Oh, wow.
the nature of dark matter, maybe even the evolution of the universe itself.
That's huge.
It's huge. It's huge.
Wow. Okay. That's a lot to process.
Yeah.
It seems like the deeper we go, the more profound the questions become.
Yeah, you're right. And it's not just about answering those questions. It's also about appreciating the elegance and the complexity of the universe.
Yeah. It's kind of humbling, isn't it?
It is. It really is, realizing how much we still don't know, but also how far we've come
Yeah.
in our quest to understand the universe and our place in it.
Right, right. Well, I'm sure some of our listeners right now are thinking okay, this is all very cool and interesting, but why should I, a non-physicist, even care about this?
That's a good question. I think it really comes down to curiosity, that desire to understand the world around us.
Right.
At the most fundamental level, everything we see and touch, the stars in the sky, the chair you're sitting on, it's all made up of these tiny little particles.
Right, so we're all just quarks.
We are essentially, so by studying these particles, we're essentially studying the building blocks of reality.
So it's not just abstract theories, it's what makes the universe tick.
Exactly. It's about satisfying that human curiosity,
Yeah.
that drive to explore and understand the unknown.
I love that.
And, you never know. These fundamental discoveries could lead to practical applications down the line. Look at quantum mechanics.
Oh, yeah.
It led to, transistors, lasers, all this technology that has revolutionized our world.
So investing in basic science is investing in the future.
It really is. You might not know what amazing technologies are going to come out of it, but history has shown that the payoff can be enormous.
It can be. It can be.
Absolutely.
Yeah.
So who knows? Maybe the research we've been discussing today will lead to some mind-blowing applications
I hope so.
that we can't even imagine yet.
Yeah, that'd be great.
It's that potential for discovery that makes this field so exciting.
Okay, before we get too lost in the future, I do want to circle back to the scientists behind this breakthrough.
Yeah.
Like, they deserve a shout out.
They do. The two papers that we've been discussing are Parton distributions from boosted fields in the Coulomb gauge by Shang Gao, Weiyang Liu, and Young Zhao, and non-perturbative Collins-Soper kernel from chiral quarks with physical masses by Dennis Bolwig, Shang Gao, Sorgato Mukherjee, and Yang Zhao.
Big round of applause for them.
Absolutely. These are the people pushing the frontiers of human knowledge.
And we benefit.
We all benefit. Absolutely.
Now, one more thing that I wanted to touch on from the article was this idea that the new research will help us understand how, like, the distribution of quarks' transverse momentum inside protons changes with collision energy. So, like, what does that even mean?
Yeah, so basically when particles collide at these really high energies like they will at the EIC,
Right.
the quarks inside experience these like extreme forces.
Right.
And those forces can really influence how the quarks move within the proton, especially that transverse motion is like, turning up the dial in the intensity.
So the energy is like a stress test for these quarks.
Yeah, it's like how do they behave under pressure?
I like it. Okay.
How
How
do
do
they
they hold up?
And by studying how that distribution of quark momentum changes at different collision energies, we can gain insights into like the dynamics of the strong force itself, how it governs, like the behavior of quarks and gluons. It's like studying a car crash in slow motion to understand, the physics at play.
The forces involved.
Yeah, exactly.
Yeah, it's like we can see the forces that make the universe work.
It really is. And one of the cool things about this research is that, it focuses on those low momentum quarks.
Oh, right. Those are the ones that we had trouble with.
Yeah, the ones that like previous calculations had a hard time pinning down, remember?
Yeah. They were like the missing pieces of the puzzle.
They were. And now we can actually predict their behavior, and that's huge.
Okay, so what does that unlock for us, being able to like actually have them in our calculations now?
It fills in a crucial gap in our understanding. So think of it like this. Imagine we're trying to understand the movement of a flock of birds,
Okay.
but our observations could only capture like the fastest birds.
Right. We'd be missing a lot of information.
We'd have a very skewed perspective.
Right.
But being able to account for those slower moving, low momentum quarks, it gives us a much more complete view of what's going on inside the proton.
It's like seeing the whole flock.
It is. It's like seeing the whole flock, not just the blur of the fastest flyers.
This is pretty exciting stuff.
It is. It really is. The pace of discovery in this field is just amazing.
It's accelerating. It's like,
It's
it's really cool to be like alive right now.
It is.
And to be watching this unfold.
Absolutely.
Before we wrap up, was there anything else that like really stood out to you about this research? Any questions or like thoughts that you're still pondering?
One thing that I find really intriguing is the potential this has for exploring other mysteries.
Okay.
So we have this tool now. We can calculate quark behavior with this amazing precision.
Right.
So what other puzzles can we solve? Could this lead to breakthroughs in other areas of physics? Like, could this help us understand dark matter or, like, the very early universe?
Those are some big questions.
Big questions, yeah.
It's like we've opened this door
Yeah.
and we're just starting to see what's on the other side.
It is. That's the beauty of scientific exploration,
Every answer leads to more questions.
Exactly. And it pushes us further down that rabbit hole of knowledge.
And who knows, maybe one of our listeners will be the one to answer those questions.
Maybe curiosity and a thirst for knowledge. Those are the seeds of scientific breakthroughs, right?
Well said. Well, we've taken a deep dive into the world of proton spin, quarks, and the strong force. I want to thank you for guiding us through this.
It's been my pleasure.
And to all of our listeners, thanks for joining us. And remember, keep questioning, keep exploring, and never stop learning.
Absolutely.
Thanks for listening.